Hello community, we have a brand new study by MIT about model stealing. We want to steal LLMs? What? Where a learner LLM tries to recover an unknown LLM model via carefully chosen queries, this is a critical problem in machine learning as it threatens here the security of proprietary models like GPT-4 and the privacy of the data that those proprietary models are trained on. So this is now a real sensitive topic here in AI research. But you will not understand anything of this new study if you have not read this study by Harvard University, Microsoft Research, and the University of California, learning hidden Markov models using conditional samples. And also, hidden Markov models are some of the most widely used tools in sequential and time series modeling. They are cryptographically real hard to learn. So if you just look at the preliminaries and you have a look here at the mathematics, you see this gets really interesting. And we have here hidden Markov models and the low rank distribution. And you immediately understand here, we are talking here about probabilistic models that specify a joint distribution over a sequence of observation generated via a Markov chain of latent states. So this is the key for us to understand this new model by MIT. Published yesterday, November 12, 2024. Now, if this works, and this is a highly complicated paper, it really poses here a significant security threat to proprietary models from, I don't know, OpenAI, Microsoft, Perplexity, whatever you have, and the privacy of the data that those proprietary models are trained on. Because I will show you this study is now opening up and says there is a way that we can re-engineer this. Is it now really possible to reverse engineer the parameter of those proprietary models to replicate their functionality just by having query access to those proprietary black box LLMs? And the answer seems to be on a pure mathematical level, yes. And we are now exposed here to a new methodology, how to do this. Now, if you just look here at chapter 6 of this new study by MIT about the learning algorithm and finding a spanner for the state space, and here the proof for the mathematical construct, and you go on and you have here, then you want to understand what is happening here, the full learning algorithm about probabilities and what mathematical space we are training this. You see, this is just 6 pages here, that it is a rather complicated study. And I tried to read this study, it's more 40 pages, and this is the state of my mindset that I was. I said, I do not get it. I'm too stupid for this publication by MIT. And I thought, how is this possible? And I looked up here the authors. And the first author here, a graduate student here by MIT, and I said, oh, great. Now I'm really stupid because, okay, I missed here the intelligence here of AI research today. And then I looked up the second person and I tell you, oh, I was so relieved. It is the Norbert Wiener Professor of Mathematics at the MIT, the director of the Data Science Center, the principal investigator of the Artificial Intelligence Laboratory. He is a Packard Foundation Fellow and a Sloan Foundation Fellow, and he is a theoretical computer scientist. So I was so relieved. I said, okay, I'm not a complete idiot. It is just a rather complex topic. And then I said, okay, yeah, of course, he's organizing here also the Harvard and MIT reading groups. And so I said, okay, so let's take this challenge. I seem that my YouTube channel here is just here about the simplest ideas. Let's here face the current AI research here with the Norbert Wiener Professor of Mathematics and his idea how we can crack open those proprietary models. So the overarching goal now of this video is to determine, can we really effectively explore and understand other closed language models in detail by only interacting with it? Specifically, we're going to look here just querying those LLMs. And you might say, hey, this might be even interesting for some friends, let's say an American group is interested how another group is building their LLMs and maybe vice versa. So you see, this topic is really important and sensitive to understand not just the mechanism, the functionalities, but also you could theoretically gain access to the training data. And this has also implication here for intellectual property and so on. So in this video here, we aim to reconstruct here or approximate here the data distribution that an existing but closed LLM uses to generate its output. So we are really trying to reverse engineer, the professor here of mathematics at MIT, to reverse engineer the LLM's behavior without direct access to its internal parameter or its internal data that it was pre-trained and fine-tuned on. Now, this involves designing now a very particular algorithm that can, just by observing here the LLM response to carefully crafted queries, learn this new model or a parallel model that closely mimics now the original LLM output distribution. So the idea, we have this idea, hey, if we just ask a model long enough in all details, we will understand here their core functionality, the way it's built up, and their training data. So I would like to show you how I failed. So here my first try. Please do not follow my first try. I will show you later my second try. But just that you get an idea. No? Now, the key to understand this are hidden Markov models. And they, statistical models used to represent systems where the underlying states are hidden. They're not directly observable for us, but, and this is the beauty, the outputs, the observation, dependent on those hidden states, they are now visible. And this is exactly what we want. No? We want to understand the hidden state here of those proprietary LLMs or VLMs, just looking here at the output of this state. So this is the mathematical framework that we're going to use to model here the sequential and the probabilistic nature of the language generation in our LLMs in the simplest case. So what we do, and this is the main idea, conceptualize now our large language model as a hidden Markov model. So we apply now a known mathematical theorem on our LLMs, and we treat the generation of each word of each token in a sequence of an LLM as a stochastic process influenced by the hidden state that we have in the layer of our transform architecture, allowing us to capture the dependencies between the words that we generate with our LLM efficiently. Professor of mathematics, what else would you expect, no? So we now focus here on hidden Markov models because they enable us, with their solved mathematical framework, to exploit here the low-rank structure inherent in the LLM distribution over the sequences. And this is one of the key insights from the second study I showed you at the very beginning of this video by Stanford and Microsoft. Please read the study, otherwise you are lost here in this topic, and I was lost in this topic. So this means now, in this distribution, this low-rank property, this is something we can use. Because it simply means that the vast number of possible sequences that the LLM could theoretically generate can now be approximated using a smaller set of hidden states or patterns, significantly reducing now the mathematical and, importantly, the computational complexity. So, by utilizing here the mathematical framework of our hidden Markov model, we can efficiently learn and approximate the large language model behavior now through elements. Let me pose 3 elements. The conditional queries, we're gonna question these hidden LLMs. We construct now compact representation like Barycentric Spanners. This is a mathematical tool I'm going to explain in a moment. And designing sampling algorithms, very specific algorithms that will maintain a statistical closeness to the original LLM. We will face, like in quantum mechanics and in quantum computation, a lot of methodologies to keep the propagating error small. And we will use some quite advanced mathematical frameworks for this. But whatever. Whenever we use this here, and this is crucial for reverse engineering the LLM distribution to understand its inner working and efficiently replicate its behavior without direct access to an internal parameter, we have 6 steps. And at least in my first try, I saw 6 steps. So at first, using conditional queries, we probe now this foreign LLM or this unknown LLM. No? So we interact with the LLM, providing it with specific inputs. These are our histories, and observing now the outputs of the LLM, so the prediction of the next token or the next sequence, whatever we are operating with. Now, each query response pair that we have now give us some information about the LLM's conditional distribution. And this means that the probabilities it assigns to possible next token given a history. And you see here clearly what door opens up to us here. but it needs here the mind here of a professor of mathematics to really put this into a working theory. So second, I showed you here in the second publication, identify the low-rank structure. Many large language models exhibit these low-rank properties due to the patterns and the redundancies in the language data, in our human language data. And by recognizing that the LLM's output distribution lie now in a low-dimensional subspace, and I would like to stress this here because this makes the computational complexity much lower, we can focus our learning on this smaller mathematical space, making the problem more tractable. And I will show you a methodology that is similar to the Fourier transformation if we use here some generating functional here on a lower dimensional subspace, but it is not a simple geometric space. Third, in my simplest idea, I thought, hey, now we construct representative vectors, no? So we have the histories and the future, so we consider sequences, our histories, and their possible continuation, which we call futures. And for each history, we create a vector that now encapsulates here the LLM behavior. No? We have now a new compressed, let's say, a vector space representation that you know already here from our LLMs of the conditional distribution over the future. And of course, since we are trying to reduce the complexity, we apply now a dimensionality reduction that you know, like UMAP. And this step reduces here the complexity of the problem, allowing us now to work with a manageable number of space dimension in a purely mathematical abstract space and has specific features. Now, central element is here computing the barycentric spanner. If you don't know it, never mind, I had no idea what it is. So a mathematical tool that helps us express any point in the distribution in our space as a combination of a small number of base points. And you say, hey, that's simple. Yes, of course it is. But if you want to read one publication I have here from Princeton University, Department of Computer Science, I would go with this one, because although it was published here in the Journal of Machine Learning Research in 2016, I think here this is a more high-level summary on volumetric spanners here. So they also go here in the keywords Barycentric Spanner, but I think this is a publication that I personally found the most helpful, the most insightful if you really want to understand what is happening here. And yeah, they explain here more about general convex set in mathematics, but more about this later. So we identify now a subset of histories whose representative vectors can be combined to approximate here the complete LLM response for other histories. So this means, and this is the beauty also, we can reduce the complexity further, that we don't need the LLM response to every possible input. We just need to choose strategically some chosen few. Because, yeah, generating functional and so on. Now, learning the transition model, this is the most complicated part, I think, here. Because, why? We combine now the estimated transition probabilities for representative history and the linear combination for other histories to build a complete transition model. So what we do, for histories not in h of t, approximate now their transition probabilities using the linear combination of those in h of t. And for each history that is inherent in h of t, we estimate the transition probabilities using our conditional queries that I already talked about. So careful, this is an important part. We combine here the representative history and linear combination of other history to form here a simplified version of a transition model. However, this enables us now to perform some sampling from the learned model. So we use now our learned model to generate sequences, simulating how the original LLM, like GPT-5, would respond to its inputs. And as we generate each token, we continuously update our model's parameter to reflect the new history, ensuring that our sampling remains faithful to the approximated distribution. And here it is important now also, as always, the error correction come in. So this was the overview for dummies like me. So this is what I thought in my first try that I thought that I would have understood about this. But as it turns out, I was just scratching the surface, because there is some mathematical optimization for a convex optimization and the Kullback-Leibler divergence. They work together as an error correction mechanism. So let's think about this in another step. And yeah, I spent more than 2.5 hours already with the paper, so I think I get a faint idea what it is all about. So the authors use here a convex optimization technique to minimize the Kullback-Leibler divergence between the distributions in our model and those of the foreign LLM. And this here really helped the author to find the best approximation at each step. So what they do, they projecting now onto convex sets in the Kullback-Leibler space, and thereby they ensure that the errors they could accumulate don't accumulate excessively as they generate longer sequences here. So it's a very nice mathematical trick to have here a convex set where the error is not going exponentially up, but we have here almost a linear additive behavior. We rigorously analyze, say the author of the study to us, how the errors propagate to our model, ensuring that the total, another important term, variational distance between our model distribution and the original or the foreign LLM remains small. So we have the main task to keep our errors small at any circumstances, like in quantum corrections. What are the implications now? I think this is important. This approach allows us now to gain insight into the decision-making processes of an LLM, which can be opaque due to their complexity. And if you would have asked me before I read this study today, is it possible to reverse engineer an LLM? I would have said no, because the complexity is simply too high. But given that this mathematical proof, and I will show you this in about 2 minutes, is valid, and I can't tell you yet because it just blows my brain, I need a second brain for this. If this is true, the answer would be yes, we can reverse engineer it. So, by learning a compact representation of the foreign LLM, we can create smaller models that approximate the behavior of the larger unknown ones. And this ability to approximate an LLM through simply querying it raises no question, of course, about the model security, and it definitely highlights here the need for techniques to protect proprietary models like GPT-4 or 5 from being reverse engineered. Because if this technique really works, my goodness, there's gonna be a lot of fun in the future of AI. Okay, imagine the training costs. Some model cost hundreds of millions of dollars. Okay, our goal is now to build our own LLM, our own model that behaves similar to this unknown huge foreign language model. So, it is a simple approach, no? We just have to ask questions. So we've strategically selected questions, but anyway, we provide the LLM with various sentences, beginnings, and record how it continues them. How here the normal process here of predicting the next token works. Then mathematical model finds here patterns. So we analyze this continuation to find patterns in how the model predicts the next word or the next phrase. And then we build here continuously a simplified mathematical model. Using these patterns, we create a model that can predict the next word in a way that's similar to the original foreign model. And now our model can now generate text that resembles that what the original language model would produce, even though we never saw its internal code or its internal training data. If this mathematical theorem holds, that is the central part I'm going to show you in a minute of this publication, this would be true. So, this work here by MIT professor of mathematics demonstrates now in a beautiful way. This is the most beautiful publication of November. You have to read this. This work demonstrates the potential to extract significant information about an LLM behavior through interaction alone. And this has important implications for AI research, for the model development, and especially to safeguard here proprietary AI systems. Imagine somebody would here have further information how Microsoft uses its pre-training data. Of course, we encountered here this low-rank distribution, and if you are not just beginning here, maybe a short reminder, think of a low-rank distribution as a way to capture the essence of complex data, just using fewer pieces of information. No? Think of a simple example. Imagine you have a library and you have thousands of songs, music. But many songs share common chords and melodies and whatever is here the minimum element of a song. And now a mathematical low-rank approximation would capture these common elements of all these 1000 songs. So in essence, you can recreate here the main melody and maybe even every song using here just a combination of basic building blocks. This is here exactly what is happening here in the low-rank distribution of our LLMs. Great. Me, I discovered I'm an idiot 2.0. Yes, I improved a little bit, but still, yeah. Gee, I have to learn so much more. I'm sorry that my YouTube channel was so simplified. It will change, definitely. Because, hey, AI research is moving up a notch. So, challenge, learning a low-rank distribution H over a sequence of a length of t from an alphabet O. A distribution is considered low-rank if, at any time t, the conditional distribution over the future sequences given the past history lie in a low-dimensional subspace. And this is here the most important part. This helps you to reduce the complexity. Common in language model where the context is often limited. Limits here the plausible continuation, the semantic context defines here there is not everything possible. So our objective is now to design an algorithm that, using conditional queries to our unknown object, our low-rank distribution H of the LLM, to learn a distribution H dash such that H dash is close, whatever closeness means in this high complexity, in the total variant distance. So you know maybe the cosine similarity as a similarity distance, and now for models here in a more complex low-rank distribution, the total variant distance is also, if you want, a kind of a measure that we use. And furthermore, we want to be able to sample here from H dash efficiently. So let's have a look at our 6 steps, a little bit more advanced now that I have some hours to understand this. And I will have to go through the complete afternoon to really understand this, hopefully, if I'm able to do it at all. Simulating access to a closed distribution H dash. So we define now a new distribution H hat that is conditionally close to H. This means that for any history H that we have, the distribution of the next character in H and H hat are close in total variance distances. And using now our conditional query to test here this foreign LLM, we estimate the next character probabilities from various histories. So by carefully sampling and adjusting these estimates, we can ensure that H hat approximate H closely, given here our distance norm. Second, we want to reduce the dimensionality using here especially representative vectors that we later use in the convex form. So for a selected set of history, H1 to HK, we sample here a polynomial number of futures, and this is a limited number of futures from a distribution D, that is a mixture of the conditional distribution given all of these histories. We define now vectors, as I showed you, representative vectors for each history H, where each entry corresponds to a sampled future. So the entries are now scaled probabilities that represent how likely each future is given the history, and this vector preserves the important properties such as total variance distance, our norm, our Kullback-Leibler divergence between the distribution, and this is all crucial for accurate approximation of H hat. Now we compute the barycentric spanner in our reduced mathematical space. Definition: a set of vectors forms a barycentric spanner if any vector VH can be approximated as a linear combination with bounded coefficients. Notice linear combination, we already encountered this. Bounded coefficients will become important later on. So we use an algorithm that identifies a subset of representative vectors that spans the space of all such vectors, ensuring that the dimensionality is kept polynomially bounded. Then we have to account for small errors due to approximation and ensure that our algorithm works even when the vectors are close to being linearly dependent. The transition model is now really the most complex part if you want. So as I showed you for each history in our spanner set, we estimate the probabilities of the next character using here our conditional queries if we are in H of t. And the learning of the transition models involves estimating the probabilities of moving from one state to the next state in a way that reflects the underlying distribution H of the sequences. And how we do this, short summary if you want, we create now a compact representation of the conditional distribution given the different histories we have. We find a small but representative set of the histories whose conditional distribution can now approximate others. Not a simple mathematical task. And for those selected history, for this minimum set now, we estimate the probabilities of the next possible symbols, word, token, whatever you have. And instead of explicitly constructing those transition matrices directly, we represent the transition through coefficients that are updated during the sampling process. 5, as I showed you, sampling from this learned representation, we generate sequences one character at a time, maintaining a set of coefficients that represent the current state as a linear combination of history in our spanner. This here is the beauty while we do this. This is here the gorgeous idea. And when moving to the next character, we just need to update our coefficients to reflect this new history. This is how the self-learning happens. This involves solving here a convex optimization problem that projects now in a mathematical space the updated distribution onto the convex hull of our representative vectors. And by projecting in Kullback-Leibler divergence space, we leverage here the property that such projection reduces the divergence to any point in the convex sets, preventing here a further error magnification and a further exponential error spread. Controlling error propagation, we have additional measures that we will take, like positivity and normalization. You know this. And now to the main idea. If you want to start, and I would recommend now, after multiple hours of this paper, Theorem 1.3. If you get this, you get 90% of the main idea. I will leave it here with you. Just shows that we can effectively learn any low-rank distribution via conditional queries. Thus, we can view our result as showing that, in some sense, the rank of a distribution can be a useful proxy for understanding the complexity of model stealing. And this is really similar, and this is amazing, to the complexity measures such as the Bellman rank that are also useful for understanding the statistical complexity of learning a near-optimal policy in the reinforcement learning of LLMs. So the crosslinks are amazing. It blows my mind what is there in this mathematical description. And maybe I need a complete weekend to just get an idea about this. If you are a god in mathematics, please, if you say, hey, that is so simple, leave us some clue in the description of this video, because I'm fighting with this publication. I understand it is beautiful, I understand the possibilities, but just the proof of this theorem 1.3 is, I don't know, I need a second brain, because currently I have, complete overflow. Great. So there you have it. If you want to see one publication in November, you have to read from MIT, Massachusetts Institute of Technology, LLM model stealing for any low-rank language model. I hope you enjoyed it. I hope I was a little bit helpful. I hope I've given you some impetus that you might become interesting to explore this paper yourself. Believe me, it is amazing. It would be great to see you in my next video.